Action. All right. So I'm going to give you a tour of probability theory today, starting with the originator of the idea, which is Pierre-Simon Laplace. And in 1814, he writes a book called A Philosophical Essay on Probabilities. And it's worthwhile to ask, this concept, philosophy, and how in the 18th and 19th century, there was no such thing as really a scientist. What there were natural philosophers. And so you guys, many of you guys, will get a PhD. And so you have a doctorate of philosophy. And the idea was that philosophy is the highest form of what mankind can do because it's thinking, as compared to what became known later as a scientist. So scientist was this kind of a lower esteemed profession because you had to collect data. You build instruments and you went out in the field and you collected data. That's what a scientist was. And it was a word that was invented in the 19th century to refer to individuals who were not philosophers. So Newton was a philosopher because he philosophized regarding the nature of the universe. And so the concept of a scientist was something that came later, and there was a great deal of debate about whether it's a good word or a bad word to use to represent, what we now think about as the daily business of science, which is to collect data, perform experiments, God forbid, to test things, because Aristotle thought that if you had to perform an experiment, it was already a bad idea. You should just think about it and see how it would work out. So in many ways, Laplace's representations and his approach to probability is based on the idea that if we knew the laws of the universe completely, then there would be no need for probabilities. It's only mankind's incomplete knowledge of the laws of the universe that makes it seem like the world is random. And so we have these rules of probability that I will describe to you, but it's going to be around and useful only temporarily until humans figure out the laws of the universe. By the time that humans figure out laws of the universe, then there will be no probable things. It'll be certainty. And we'll know for certain how things are going to happen. So that's the notion of probabilities as far as Laplace was concerned. So he described probabilities in three components. And I'm going to start with the first component. And it has to do with what is a probability. So probability is the ratio of a favorable event to that of all possible events. So suppose that we have two throws of a coin. So two throws of a coin, and we want to know what is the probability of getting exactly one head. And so here's my first time that I throw it, here's the second time that I throw it. And so what are the combinations that I could get? I could get a head and another head, a head and a tail, tail and a head, or two tails. And so probability of having head exactly one, given that I have two trials that I've thrown it, is equal to, here's one case that I succeeded, here's another case that I succeeded, so 2 out of 4 times. So the probability of getting exactly one head by throwing a coin twice is 1/2. So definition of the probabilities is clear, right? It's the ratio of getting probable probability of something is the ratio of getting a favorable event, whatever that favorable is, to the total number. Now, as I mentioned to you, Laplace viewed probability as a reflection of our meager knowledge. So he said that, in fact, he thought every event is fully determined by the general laws of the universe. So there is no such thing as probability, which brings us to this, Einstein's famous quote that, God doesn't play dice with the universe. So the way to think about probabilities, the way Laplace described it, is that if we knew the position and velocity of every particle in the universe at any moment in time, we would know the entire future of the universe, as well, of course, with the requirement that we knew the laws of the universe. And so he said that so it is that we owe to the weakness of the human mind one of the most delicate and ingenious of mathematical theories, which this is the science of chance and probabilities. So this idea that probabilities arise because of our lack of knowledge of the laws of the universe pervades even the 20th century. So I don't know if any of you guys have read some of the work of Isaac Asimov. He, in the Foundation trilogy, his most famous work, describes a future where scientists are able to predict that the galaxy is going to fall into chaos. And the way they do it, mathematicians, they do it based on looking at, the current state and predicting into the future what's going to happen. And based on that, this ability to predict into the future, they take charge. They try to save the knowledge that was acquired, and that becomes the basis for that particular story. All right, so that's what a probability is. Now, let's move on to the second concept in Laplace's description of probability, and that's the concept of independence. So, if events are independent of each other, then the probability of their combined existence is the product of their respective probabilities. So you have two dice, and you throw them, and so the probability of the first dice giving you a 1 and the second dice also giving you the 1, if these two dice are independent of each other, that's the probability of the first one giving you a 1 and the probability of the second one giving you the 1, which, if these are fair dice, this is 1/6 squared, which is 1/36. So Laplace used this concept to go over a very simple idea in history. he said, suppose that you've had some event in history that you believe to be true. And suppose that event was transmitted through 20 people. So 20 people, one told the other, the second person told the third person told the fourth, and by the time it got to the 20th person, that was you. That's when you heard about this event. And so he said, if you view this process of transmission of information such that in every instance in which that event was described, it was 90% accurate, then by the time that that event reaches you, the 20th person, it's surprising, but then that probability of it being accurate falls considerably. So suppose we have a random variable. It can take on the value of 0, 1, and that the probability of this random variable taking the value of 1 is 0.9. So 90% of the time is going to be true, what they tell you. So if you now look at the sequence of events that started with x1 being equal to 1, x2 being equal to 1, and what is the probability that by the time it got to you, the 20th person, it is still 1? And Laplace writes that if you look at this probability is 0.9 raised to the power of 20, which is only around 1/8. So he said, based on this, that a lot of things in history that we take for granted as being true is unlikely, in fact, because of the fact that even if it was highly reasonable that one person will accurately describe what they saw to the next person, degradation over time will make it unlikely that what you hear now has any resemblance to what occurred before. And of course, if you think about it, in the court of law, this is why hearsay is not admissible, right? Hearsay refers to the fact that you heard somebody say something about something that they had seen. That's the second observation of Laplace. All right. Any questions so far? All right. So the third observation. The third observation that he made, the third principle, is the principle of conditional probabilities. So the idea of a conditional probability is that when two events depend on each other, the probability of the combined event is the product of the first event and the probability of this event having occurred. Second one will occur. So the idea is that if we have a random variable x and it can take on a value 0, 1, let's say, and we have a random variable y that also can take on a value 0 and 1, then probability of x being 1 and y being 1, that's equal to probability of x being 1 given that y is 1 times the probability that y is equal to 1, which is equivalent to saying the probability of y being 1 given that x is equal to 1 times the probability of x is equal to 1. So let's do an example of this. Suppose we have 3 jars. Let's see if I can reduce this a little bit. Okay. So suppose we have 3 jars, And what we know is that 2 of the jars have white balls, and the 3rd jar has black balls. Okay, so this is what we know. What we do is that we take a ball from jar C. We want to know what's the probability of that being white. So we have A, B, and C as our jars, and we're going to enumerate the conditions for it. So suppose that we say 1 means it's got a white jar and 0 means it's got a black jar. So suppose that's our case here. We could have something like this, or we could have something like this, or we could have something like this. These are the 3 conditions that are possible. So 2 of the jars have white and 1 of the jars has black. So what's the probability of picking a ball from jar C and getting it to be white? What's the probability of C is equal to 1? Well, here's one condition. Here's another condition, so that's 2/3. Right? So how does this tell us about conditional probabilities? Well, suppose now what we do is that we have drawn a white ball from jar C. What we want to know is that what's the probability of drawing a white ball from B? So what is the probability of B being equal to 1 given that C is equal to 1? Well, you can look at it here. So C is equal to 1, and there are 2 conditions. What's the probability of B is equal to 1? Looks like it's 1/2. So can we drive this representation? Can we get this answer using the rule we just learned? So this is equal to the probability of B equal to 1 and C equal to 1 times 1 over probability of C being equal to 1, right? So the conditional probability is the joint probability divided by the probability of the event itself. So that's equal to the joint probability of both of them being equal to 1. It only occurs once. So that's 1/3. Probability of C being equal to 1, we just did up here, is 2/3. So that's 1/2. Which brings us to Bayes' rule. So Bayes' rule, an important rule that we're going to be using later when we do inference, comes from the conditional probability observation. So the probability of x is equal to 1, y is equal to 1, that's equal to the probability of x is equal to 1 given that y is equal to 1 times the probability of y is equal to 1, which is also equal to the probability of y is equal to 1 given x is equal to 1 times probability of x is equal to 1. So now we can write the probability of y is equal to 1 given x is equal to 1 is related to probability of x is equal to 1 given y is equal to 1 times probability of y is equal to 1 divided by probability of x is equal to 1. Yeah? All of you guys have seen this before. Okay. Okay. Let's do an example. Suppose we have a group of people where 40% are male. And among these 40%, we know that 50% are smokers. We have another group of people in this group of people, we have 60% that are female, and among these 60%, we have less probability, 30% are smokers. And our objective is to understand something about the probability that a smoker is a male. So X, you could be male or female. Y, you could be smoker or non-smoker. And what I want to know is that if I tell you somebody's a smoker, what's the probability that they're male? So let's see if we can solve this. So the probability that you have a male conditioned by the fact that he's a smoker is the probability of being a smoker given that you're a male times the probability that you're a male divided by the probability of being a smoker. So this quantity, the conditional quantity, probability of being a smoker given that you're male, what is this value? What's this probability?
50%.
Very good. 2.5. And what's the probability of being male?
40.
Okay, so now let's compute the probability of being a smoker. So the probability of being a smoker, that's equal to the probability of being a smoker given that you're a male times the probability of being a male plus the probability of being a smoker given that you're a female times the probability of being a female. So this quantity here is equal to 0.5 times the probability of being a male is 0.4 plus being smoker, given that you're a female, it's 0.3 times probability of being a female is 0.6. Okay, so and this turns out to be something like 0.38. Okay, so now we're ready to figure this out. So this quantity we know, and so we divide this up, and I think you get something like 0.53 or something like that. So that's the solution to our problem. Did you see how I did it? The interesting thing was the denominator. Where we integrated over all conditions. Okay. Let's do some algebra of random variables. So the important elements of this algebra are the moments of the distributions of the probabilities. So we have things that we're going to call means, which are the expected values. Of the random variable, the expected value, and of course the variance. So I'm going to start with scalar random variables, and then once we figure out the scalars, we'll do vectors. So what is an expected value of something? So the expected value of a random variable x, that's equal to all the conditions where that x occurs times its probability density at that location. So x going from minus infinity to infinity summed up and weighted by the probability. So little p represents the density, capital P, probability, PR is what we call, probability of something being a particular value. So you weigh your random variable by the value of its density. We often write this also as x bar. The variance and the expected value are going to be the tools that we're going to use a lot. So when you have a scalar times a constant, so this is a constant, the a is a constant, x is the random variable. So that's going to be, it's just simply equal to a, right? If you look at the sum here, a comes out of the sum, that just becomes a times expected value of x. So if you have a constant that multiplies by a random variable, its expected value is just that constant times the expected value of the random variable. All right, variance. So variance of x is defined as the expected value of x minus its expected value squared, which is equal to expected value of x squared minus 2 times x times expected value of x plus the expected value of x quantity squared, which is equal to the expected value of x squared minus, I'll bring the expected value inside. This is the random variable now, x, so I get minus 2 times the expected value of x quantity squared plus the expected value of x quantity squared, which is equal to expected value of x squared minus expected value of x quantity squared. So what this means is that you take a random variable, you square it, and you find its mean. Then you take that same random variable, you find its mean, and now you square the mean. So variance is the difference between the mean of the squared random variable minus the mean of the random variable squared. Based on this, we can say that variance of a constant a times x, so again a is the constant, x is the random variable, that's equal to the expected value of ax minus ax bar, that's the mean, squared, which is the expected value of a squared x minus x bar squared so that's a is just a constant, so it comes out. Which is equal to a squared variance of x. So variance of constant a times x is a squared times variance of x. Okay, oftentimes we do something that looks like this. We want to minimize something called the mean squared error. What is that? That's the expected value of the random variable x minus our estimate squared, x hat. So in this case, this is the random variable. This is the constant. So what is x minus x hat squared? Well, let's look at that. That's the expected value of x squared minus 2x x hat plus x hat squared, which is equal to the expected value of x squared minus 2 times the expected value of x x hat plus x hat squared. So this term here, I can replace the expected value of x squared with the variance. So look at this. Variance of x is expected value of x squared minus expected value of x quantity squared. So I'm going to replace the expected value of x squared with variance. So that's variance of x plus expected value of x quantity squared minus 2 times expected value of x times x hat plus x hat squared. Did you see what I did? I replaced this quantity with the variance plus its mean squared, because that's the definition of variance. So what I have now is that I have variance of x plus, look at this term. This is a perfect square. Expected value of x minus x hat squared. So we started with expected value of a random variable minus my estimate of it. What I get is that that's equal to the variance of the random variable plus my bias in estimate of that random variable. So the error in estimating a random variable depends on the variance of that random variable and my bias in estimating that random variable. Okay. All right. So I'm going to next show you how we can apply our expected value and variances to some random variables and some experiments that have done things like that. So let's begin with discrete random variables. So discrete random variables are things that take on, discrete quantities. So again, x, say, is our random variable, and it can take on a value of 0 and 1. And we know that the probability of x being equal to 1 is equal to q. So if I draw for you the probability density function, it would look like this. So x can take on two values, 0 and 1. At 0, the probability density is q. At 1 minus q. At 1, its height is q. So this is the density function for this probability. So now how can I write this density, p of x? What does that look like? Well, my density is such that when q is equal to 0, the probability is 1 minus q. So I have q, and I have 1 minus q, and this should give me the density. Let's see what I did here. I said, take x. What is the value of x? Say value of x is 0. If value of x is 0, q to the x, something raised to the power of 0 is 1. 1 minus x is 1, because x is equal to 1. So then the density, when p of x, when x is equal to 0, I just get this term here, 1 minus q. That's this height, 1 minus q. When x is equal to 1, this term goes away. I just get this, q to the 1, which is this. So I was able to write the density of this discrete random variable using this equation. Does that make sense? Okay. So now what I'm interested in is the quantity n, which is equal to the number of times the event was positive, was 1. So say that there are n events, I events, where I've looked at this quantity x, and I want to know what's the expected value of how many times x was equal to 1. So say x is a coin. 1 means that you get a head. You've thrown the coin n times, capital N times. You want to know what's the expected value and variance of the times that you're going to get successes. So what I want to know again is I want to know what is the expected value of n, what is the variance of n. These are what's called Bernoulli trials. But we're going to derive this using the concepts of variance and mean that I saw. So again, n is this number of times that you got a positive result, say a head. And that's just, of course, the sum of xi. And x is equal to 1, you get a positive event. So sum it up, and you get the little n here. And you want to know what's the expected value. And of course, that depends on the probability of getting one of these correct trials. So we're going to see what that works. So let's say we have just one trial. So suppose I only have one trial. So in that case, expected value of n is just equal to the expected value of x. So because capital N, so that means capital N is just 1. Well, what's the expected value of x? That's equal to the sum of x times p of x. So x can take on two values. 0, the probability of getting 0 is 1 minus q, plus you can take on the value 1, its probability is q. So that's equal to q. Just going back, this was our probability. This is the density function. So at 0, the probability is 1 minus q. 1, the probability is q. So the expected value of n for just one trial, if you only had one trial, then that's just the expected value of x, which is q. What's the variance of n? So I want to show you that you think about variance as something that you have to have multiple trials for, but that's not true. You don't need multiple trials to estimate variance if you know the density. So we're going to see that despite the fact that I only had one trial, I will not just have a mean, I will also have a variance. So what is that variance? What's the variance of n? That's equal to the variance of x. And that's equal to the expected value of x squared minus the expected value of x quantity squared, which is equal to, expected value of x was q. What's the expected value of x squared? So this quantity is related to the variance, right? So let's compute that. Expected value of x squared is the sum of x squared times p of x, right? Which is equal to, x can take on two values, 0 squared. What's the probability at 0? 1 minus q. Plus, you can take on a value 1 squared. And what's the probability at 1? Q. So that's equal to q. So expected value of x squared is q. This term is q minus expected value of x quantity squared. Expected value of x is q. So this is q squared. That's the variance. From one trial, we have the variance and the mean of a random variable. What if we had n trials? Not 1. Something greater than 1. So now n is the sum of I equal to 1 to n of x of I. That's the number of times that our event gave us a positive value. So what's the expected value of n? Now that's equal to capital N times the expected value of x, which is equal to n times q. What's the variance of n? This is n times variance of x, which is equal to n times q minus q squared. Okay. So now let's use what we just did to look at an interesting example from the literature where they did statistics to try to infer a particular condition. So I'm going to tell you about a patient. This patient was named PS. So patient PS. What was interesting about the patient is that this patient had right side lesion of the brain. Which caused left neglect. And this particular patient was described in a paper that appeared in Nature. Yeah.
It should be n squared, right, for the variance? Or
Well, n, so variance of n is just the variance of this equation. And so it's n times variance of x, not variance of n times x. So it's a good question that you ask, but I think this is correct. You see why? Because it's n times variance of x.
Because x are independent.
Because x's are independent of each other. Yeah. Thank you for that question. Okay. So there was this patient named PS. The patient had right side of the brain lesion. And what happened to her is that she had what's called neglect. And here's what neglect looks like. So the reason why I'm telling you about this particular story is because we're going to see how they did statistics on one person. So by knowing probabilities, we'll be able to tell whether the effect that they saw is reliable. So here's this patient. The patient is given a task to do. And so what neglect means is that when you see an object, say a house, there's a house. In this object, when the individual looks at this object, they direct their attention largely to the right side of this picture. Of course, they can look anywhere they want, but their attention is drawn to the right side. That's what left side neglect means. So if you ask such a patient to copy an image of a clock, they will copy the numbers on the right side and not draw the numbers on the left side. That's a typical example of what neglect would be. So in this paper, they're trying to describe to you what neglect is, but they only have one person, they only have one patient, right? So they're gonna do statistics on one person, and we're gonna see how that's possible. So this patient sees two kinds of houses. A house like I'm showing you here, and a house where the left side is on fire. Okay? So ask the patient, is there a difference between these two houses? And the patient reliably says that the pictures are identical. However, when they ask the person, which house would you like to live in? The patient picks the house that's not on fire 14 out of 17 times. So what I want to know, is this a reliably significant difference from chance? And so let's write the statistics of what a random pick individual would do and compare it to this individual. Let's see if we can tell the difference. And going back, it depends on these guys here. What's the mean and what's the variance? And by knowing the mean and the variance, we'll be able to put confidences about the choices. And then we'll see that indeed 14 out of 17 is different from chance. And that's the message of this particular part of our little presentation. So, okay, so we have random variable x. It can be 0 or 1, and let's say 1 means I'm going to pick the house not on fire. And all we know is that this patient had picked in such a way that the house that was on fire was picked 3 out of 17 times, and the house that was not on fire was picked 14 out of 17 times. So we write that the probability of picking the house that's not on fire is 14 out of 17 times. So that's the probability of our random variable based on our observation of this patient. So now what I want to know is that what's the expected value and the variance of this random variable. So the expected value of x is, of course, just the number of times times the probability. In this case, it is going to be 14 out of 17, q, right? Expected value of x is just q. Whoops. The variance of x is q minus q squared, which in this case is going to be 0.15. Here's q, the probability of it being success. So we have a random variable. In this case, the probability of it being successful is 14 out of 17 times. That's its expected value. The variance of that random variable is 0.15. All right. So now what we want to know is n, which is number of times she picked the house not on fire, which is the sum of I is equal to 1 to 17 of x of I. So we made 17 observations of the random variable x. And what is the expected value of n? That's n times expected value of x, which is, of course, 17 times 14 over 17, which is equal to 14. So we should have seen 14 times that she picked, on average, the house not on fire. And of course, that is the case because that's what our probabilities were. What's the variance of n? So now this variance is the critical variable because it's going to tell us the confidence that we have. That's n times the variance of x, which is 17 times 0.15, which is 2.5. So typically, what we care about is our standard deviation. The standard deviation of n is going to be the square root of 2.5, which is about 1.6. Okay, so this is what she did. We have a random variable that describes her behavior. It has a mean of n, 14, and it has a standard deviation of 1.6. So do you see, even though we just measured something once, because we have a probability distribution that we assumed, we have a mean and we have a standard deviation. Now what I want to know, is this reliably different than chance? So we have to now describe our alternate hypothesis. What's our null hypothesis? Well, a null hypothesis is that this was done simply by chance. So that means we have a chance behavior. And she could have picked one house or the other with probability of 1/2. That's our probability density function. So in our chance behavior, probability of picking the house that's not on fire is 1/2. The expected value of x is 1/2. The variance of x is q minus q squared, which is 1/4. And if you have 17 trials where you've looked at the behavior, the expected value of what you should see is 17 times expected value of x, which is equal to 8.5. The variance of your observation is 17 times 1/4, which is equal to 4.25. The standard deviation of n is about 2.1. So here's what we have. So our mean here for our null hypothesis is 8.5. Its standard deviation is 2.1. Our observation had a mean of 14 and had a standard deviation of 1.6. See? So now I can do statistics. I can compare this person's behavior, which had a mean of 14 with a standard deviation of 16, with my null hypothesis. So my data is here, 14 plus or minus 1.6 and my null hypothesis is here, 8.5 plus or minus 2.1. Okay? So you can do statistics on this now. So based on the distance between the means and these particular standard deviations, you would infer that these are reliably different. Do you have any questions? So this is how we do discrete random variables. All right. Expected value and means of these discrete random variables. Okay, our last topic, algebra of random variables. So oftentimes we have two random variables, x and y. Say we want to add them. And so what is the expected value of this quantity? That's going to be the expected value of x plus the expected value of y. What's the variance of x plus y? That's the expected value of x plus y minus the expected value of x plus y, quantity squared, which is equal to the expected value of x minus x bar, its mean, plus y minus y bar squared. I just rewrote this, replacing expected value of x with x bar. So that's equal to the expected value of x minus x bar squared plus 2 times x minus x bar y minus y bar plus y minus y bar squared, which is equal to this quantity here. What is this quantity? What's the expected value of x minus x bar squared?
The scores should be inside the expected value in the first one.
Thank you.
And also the first line.
So what's the expected value of x minus x squared? I want to take this expected value, bring it inside the brackets. What's this term here? Good. Variance of? Variance of x, right? That's what this term is. Expected value of x minus its mean squared is variance of x. Okay, plus I get this term here. This is called the covariance of x and y. Plus, what's this term? Say again? Thank you. Right. So variance of x plus y is the variance of x plus variance of y plus covariance. And so if two random variables are related to each other, they will have a covariance, which is defined by this term up here. The covariance of x and y is equal to expected value of x minus its mean times y minus its mean. Okay? So if things are uncorrelated, the covariance is 0. So if I have a vector random variable, so x being composed of x1, x2, blah, 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 that's a vector, then the expected value and variance of the vector, particularly the variance is of our importance to us, variance of this vector is going to be the expected value of x minus its mean times x minus its mean transpose. So variance of a vector becomes a matrix. And that's called the variance-covariance matrix. And this is going to be equal to the expected value of this vector x transpose minus the expected value of x times the expected value of x transpose. So all of this time, I didn't put a underline my x's, but these are all vectors. So when I have variance of A transpose x, this is a scalar quantity, right? Because I'm taking a vector x, multiplying it by a vector A transpose, so I get a scalar quantity. My variance is also a scalar quantity. A transpose variance of x times A, where A and x are vectors. So variance of a scalar quantity is a scalar quantity. A transpose variance of x times A. Variance of a vector quantity, matrix A times x, this is equal to variance of a vector quantity is going to be a matrix. And now it's going to be A times variance of x times A transpose. I have worked this stuff out in the notes that you have online. That'll help you for the homework for tonight. The homework for tonight is going to cover the ideas of conditional probabilities, independence of probabilities, and whether there's covariance and how it influences those things. So of particular importance to us for remembering where we're going is that be comfortable with what is the definition of a variance, its relationship to the expected value, what happens when we take vectors and multiply them by each other. When we want to describe variance, we take matrices and multiply them by vectors. What we do with them, we're going to do this a lot. We're going to do a lot of basically algebra on random variables and finding its means and their variances. So we'll have lots of time to practice these kinds of things. Any questions? Yeah.
For the variance of ATX,
Yeah.
when you can move the variance of x to the front, and then A transpose A is the norm, right? Or
No, so this is, you can't move that in the front because this is a matrix.
oh, okay.
This is a vector. This is a vector. This gives you a scalar, right? All right, guys. Thank you so much. Did I do something?
Just stop recording.
Oh, I shouldn't have quit. It was slower today. It was a little bit harder. So I don't know, just so you know.
Oh, we might have lost.
You might have lost.
What should we do? He wants to stop the recording before the ice can. Okay.
So you saved it.